So now we shall consider within the transition state theory the calculation of the reaction rate, transition rate from one basin to the other, from the reactant basin to the products basin, in the general case of the multi-dimensional potential energy surface. So on this sketch here, we have one basin shown and another. So these are coordinates of our system. Of course, I can draw only two. And the vertical axis, which is out of the screen, it shows the potential energy surface. I introduce a function f of the all coordinates of the system Q such that this function is negative in the reactant basin and it is positive in the product basin. And the function is equal to 0 on the dividing surface separating the two potential energy minima. We choose this function in such a way that its a normal derivative along the dividing surface in the direction from the reactants to the basin will be equal to +1. So we can imagine that if we stand anywhere before the dividing surface in the reaction basin, we will fall into the reaction basin. If we stand outside that dividing surface but on the side of the product basin anywhere, we will fall into the product basin. So according to the transition state theory, we will overcome the barrier from the reactant basin and find ourselves in the products basin if we reach any point along the dividing surface with the general velocity directed towards the reactant basin. First of all, we choose a small surface delta S on our dividing surface. Then the flux through that surface area over the time delta t will be given by that expression. Here n is the normal to the surface directed that way from the reactants to the basin, and it can be written as the gradient of this function f of q. V here is the multidimensional vector of velocities of all particles. So here we have a dot product of these two vectors. So the total flux to the right, so from the reactant basin into the product basin, will be given by integral. So we have to integrate over all dividing surface, over all ds, so this surface integral over the dividing surface, and we have to integrate over all velocities. So here v grade dot product with the gradient, this is that term vn, but we also need to multiply this by that condition. This is the Heaviside function of a dot product of velocity and the normal to the surface. It is positive only if the multidimensional vector of velocities is directed towards the product basin, anywhere you stand on the dividing surface. In that case, the Heaviside function is equal to 1. If that product is negative, so the velocity directed anywhere into the reactant basin, that Heaviside function is equal to 0. So this is the way in this multidimensional velocity integral to take into account of the fact that we would like to calculate the flux only to the product basin. And here is the canonical distribution. And again, as in one-dimensional case, it's a function of the velocities, of course, but we calculate it all on the dividing surface. We, of course, take the integral over the surface, so we take account of the flux coming through any point qs on the dividing surface. Okay, so far this is just a generalization of our one-dimensional case. Now let's have a look at this probability to be on the dividing surface. That probability is given exactly as in the one-dimensional case by the canonical distribution. So this is the Hamiltonian of our system, calculated at that point on the multidimensional dividing surface. depends on the velocities because the kinetic energy is there as well, and Zr is the partition function, which is calculated only within the reactant basin. This is exactly what we did in the one-dimensional case as well. And this is done by simply introducing this another Heaviside function of minus function f. So that function f is negative when it is in the reactant basin. So this minus that function is positive, and therefore all the q values which correspond to this f function being in the reactant basin would be included. However, the points q of the multidimensional phase space, which correspond to the positive value of the function f, would correspond to the negative argument of the theta function, and therefore will be excluded. So we integrate here only within the reactant basin via introducing this clever function f of q. Then this surface integral here can be replaced by the volume integral. We can do this, so this is the q is the volume integral over the whole volume, by introducing this delta function of that function f of q. So that delta function would explicitly include only those values of q for each f of q function is equal to 0. So it will be only exactly on the dividing surface. So q will be on the dividing surface only. So combining all these results together, we obtain the following expression for the transition rate per unit time. So this we divide by the total flux, we divide by time. So in the numerator, we integrate over the whole phase space. The delta function takes care of the fact that in fact this is a surface integral. So we need to pick up only those q values for which this function f of q is 0. Then here we have a dot product of the velocity and the normal to the surface. This comes from the expression for the flux. This is the exponential factor from the canonical distribution. And this Heaviside function picks out only those velocities which are directed from the reactant basin into the product basin anywhere on the dividing surface. And by the way, the Hamiltonian here is also calculated on the dividing surface. In the denominator, we have this partition function Zr of the canonical distribution, and this Heaviside function here allows us to limit this integral over those regions of the q space which correspond to the reactant basin only. So in this expression for the rate, we assumed that once we reached anywhere the dividing surface and our multidimensional vector of velocities is directed towards the product basin, then this is successful, and this has to be included in the calculation of the rate. This is what has been done. But in fact, in reality, this is not always the case, because if you consider a trajectory of the system which reached the basin, it can return back into the reactant basin. So these coming back trajectories are not included, and therefore this transition rate will be overestimated. In order to have a more realistic expression for the rate, which goes beyond the transition state theory, one has to correct it. And this can be done by running molecular dynamics simulations, say starting at random at different points of the reactants basin, calculate the ratio of the trajectories which pass the dividing surface and do not come back to the reactant basin to the whole number of MD trajectories considered. This ratio would give us the required prefactor, which will be between 0 and 1. In that expression we have obtained, we have this integration over the velocities. In fact, this can be, fortunately, calculated analytically exactly, and one can arrive at the expression which doesn't contain at all the velocity integrals. So let me explain you how this can be done. So what we do now, we simply calculate these velocity integrals only in the numerator and denominator. So the q integrals are calculated here last, and therefore for the velocity integrals, the value of the q vector is fixed somewhere. So in the numerator, we have this velocity integral to calculate, This is the kinetic energy here in the exponent. This is the Heaviside function to ensure that velocity is directed towards the product basin. And this is the dot product of the velocity and the normal to the dividing surface. In the denominator, we have a simple integral just of the kinetic energy in the exponent. To calculate the numerator integral, what we do first, we rescale the velocities. We introduce, instead of the vector of velocities, vector tilde, v tilde, with the mass, such that kinetic energy term would become simply v tilde squared, and would therefore be a square of a length of a vector v tilde, which is invariant with respect to the rotations in the v tilde space. The Jacobian of transformation between v and v tilde is simply 1 of the square root of the determinant of the matrix M, which is easy to calculate because the matrix M is the diagonal matrix of the masses. So now let's look at this integral. So we use Jacobian to replace v with v tilde. So we have this here. Kinetic energy term, this one, becomes this one, and we see the kinetic energy, we don't have masses anymore. The dot product of the v and the normal to the surface is replaced by the dot product of the v tilde vector and the vector EQ, which adsorbs this m minus half mass. Next, this Heaviside function similarly is written as a Heaviside of the same dot product of v tilde in EQ. Now comes a very nice trick. These terms are very difficult to calculate, it seems, but in fact, if we rotate a coordinate system, v tilde coordinate system, in such a way that the first component, Cartesian component of this vector v tilde, would be directed along the EQ vector, then this integral is easily calculated because these two terms will be easy to interpret. So vector EQ for the given Q on the dividing surface is somewhat directed, not necessarily a normal, because we have this prefactor here as well. But our first component of this new vector v tilde after rotation becomes parallel to this EQ. So our integral here now have the following form. So first of all, from this dot product, we have a product of the v1 tilde component, this one, and the vector EQ. But because they are parallel, there's no cos between them. So we simply take the absolute value of EQ out, divided by this prefactor of the masses. Then we integrate over all v tilde space. So this v tilde dot product would give us v1 tilde, just an absolute value. And this theta function would simply be theta function of v tilde 1. So it will be non-zero or equal to 1 only when v tilde 1 is positive. The kinetic energy term would become this one because it is invariant with respect to any rotation in v tilde space. Because we have here, as was said before, a square of the length of the vector v tilde, which is invariant under any rotation. And this integral is easy to calculate. First of all, this is a multidimensional integral. It contains a dimension v1 tilde and all other dimensions. So let's select this v1 dimension first. So this will give us this expression. So it will be v1, and from this dot product in the exponent, we will pick up v1 square tilde. So this that contribution of v1 tilde into this kinetic energy. And we integrate from 0 to infinity because of this Heaviside function. All other components, all other 3n minus 1 components of the velocities, they simply be written like this, which comes from the kinetic energy in the exponent. So these are Gaussian integrals. This is a simple integral we already encountered before. It is calculated by taking this exponent as a new variable. And if you perform this integration, you will arrive at this very nice, simple result. 3n is the total number of degrees of freedom of our system. So this is the integral in the numerator. Now let's consider the integral in the denominator. That is one very simple, because there is no conditions imposed on it at all, and therefore we can perform the integration over all degrees of freedom at once, and this is the result you get. This is just a Gaussian integral. So the ratio of the two, which appears here, is given by this. We can introduce this ratio because the contribution of this term in the denominator does not depend on the q. Remember, these q integrals are meant to be calculated after the v integrals, both in the denominator and the numerator. In the numerator, the v integral does contain q in this absolute value of the eq vector, but in the denominator it doesn't. It's just a constant. Therefore, we can take this constant out of the q integral and put it inside the denominator, and therefore this ratio appears. So, concluding what we have just done, we can remove the v integrals altogether, and what we will find is that the rate comes into that expression, which contains only the q integrals, volume q integrals over the whole space. The integral q integral in the denominator contains this heaviside function to constrain the integration to the reaction basing only, and here is the potential energy only. In the numerator, we have this integral, so this is the absolute value of the EQ, which we have coming from the velocity integral. This b factor comes from the velocity integral. Again, this is a exponent of the potential energy, and this delta function is introduced to limit our integration to the dividing surface only. So this integral in the numerator can also be written via the dividing surface reactive